Okay, so today we will continue the discussion on distributed file systems. Last time I spent quite a bit of time talking about NFS, okay, just to get us familiar with the basic concepts in distributed file systems. Today I'm going to talk about actually three different file systems. We'll talk about Coda, okay, which is a file system designed for mobile client access. I'm going to talk about XFS, which has a very different philosophy of doing this, implementing distributed file system. It's actually almost like a peer-to-peer distributed file systems. In that context, I'm going to introduce two concepts, which is RAID, redundant array of independent disks, and I'm going to talk about log structured file systems. They both are incorporated in XFS. They are both independent systems, but they come together in XFS in a nice way. I'm going to talk about HDFS, which is a file system that's used in Hadoop. If you use MapReduce or Hadoop, you know that there's something called HDFS. I'll very briefly touch upon HDFS and talk about object storage system. And given that we are talking about 4 or 5 systems, we'll do it at much higher level of detail, but you will still get the high level idea of what each of these file systems do. Yeah, we'll start with XFS, not XFS. We'll start with Coda first. Okay, so Coda is a distributed file system that is it was a project that came out of CMU about 15-20 years ago now. Okay, so it's not a very new project. It's been around for a while, and the main motivation for Coda was to design a file system for mobile clients. Okay. Today, mobile clients are pervasive, but think about 20 years ago when laptops were not very popular. But they thought that the future world is going to be one where you will have lots of mobile devices accessing data. And the question was, how do you design a distributed file system that is specifically tailored to the needs of mobile devices? Okay? So, what does mobile device bring to the table that changes this design of file system? The main thing that Coda worries about is this notion of disconnection or weakly connected lines. Okay, so the idea is if you have any mobile device, okay, it may, let's say you have a laptop and then if you use Wi-Fi to connect to your network, there will be periods of time where your Wi-Fi, where you do not have any Wi-Fi access. Your laptop is no longer connected to the network. Okay, so maybe you go from the department and go home while you are traveling between the office and your home. You are not connected to the network. Maybe you go on a plane ride and maybe you don't have network connectivity when you're in a plane ride. Okay, so there will be often scenarios where you are going to be disconnected from the network. Okay? And then the question is, what can you do from a file systems perspective to help users continue to make progress and do their work? Okay? You could simply say, you are not connected to the network, you cannot have access to your files, in which case users are not going to be able to do anything. Okay? But on the other hand, if you can intelligently cache whatever data the user needs and then continue to access that, they provide access to the data while they're disconnected, you can actually be more useful from the user's perspective. So what Coda has is a file system cache that is used in some interesting ways, as we will see. Okay? So the file system cache basically keeps track of all the files that a user is interested in and allows you access to that file cache even if the user's device is disconnected from the network. Okay? So the closest analogy, there are two analogies you can think of. One is if you think about webmail. You may have Gmail or Yahoo or any of these webmail systems. If you don't have network connectivity, you cannot access your mail. Okay? Now, Gmail has a disconnected mode, which I don't know if any of you use, but if you use that, it will cache your files for you. Okay? Standard mail clients do this all the time. If you use mail clients like Outlook or Thunderbird or Mail, the Apple Mail client, it will automatically keep a cache of your email with you. So even if you're disconnected, your mail is always on your machine. It's in a cache and you can make modification, you can send, receive. When you can't receive, you can send. But all of that is queued up, and when you connect at a later time, you are going to talk to the server and resynchronize. Okay? Those principles actually were first designed in the context of Coda's file system. That's exactly what happens in Coda. you have a file system cache, your files are stored on your local device. Okay, not all of them, only files that the user explicitly wants or anything that the system has learned. The system learns what files users care about and continue to access or continue to cache them. When you go away, the system disconnects, but your cache is with you, so you can get access to your files. So it almost looks like you are connected. Okay, there is no disruption because you don't have any network access. Okay, only if you try to access a file that is not cached will you get an error. Otherwise, everything looks exactly the way it looks. When you are connected, you continue to access files, make modifications. When you rejoin the network, you are going to run a resynchronization protocol and send any updates from the client to the server and pull any updates back from the server to the client. Okay, this is basically the philosophy. Yeah. There are lots of issues we'll have to deal with in designing Coda, which is what to cache, how to ensure consistency of data between the file cache and the servers and server replicas and so on. Okay, that's basically what we are going to discuss. Any questions about motivation? Okay, the main thing to keep in mind is this is a file system designed for mobile clients. Okay, and so we'll talk about disconnections and so on. Okay. So here are some design level decisions. So first, Coda has this notion of a volume. Okay, volume is a set of files that are logically part of that volume. Okay, so each file is going to belong to exactly one volume. And the important thing in Coda is volumes can be replicated. Okay, in NFS, we didn't actually talk about replication. We said there's client and server. NFS has some concept of replication, but this is highly prevalent in Coda. Each volume can be replicated on multiple servers. So you will have two file servers showed here. You can say here are the set of home directories. Replicate them on these two servers. So both of these servers will have copies of your files in your home directory. If one server goes away, it still remains in the other server. Okay, so there is replication going on, but that also means you have to ensure consistency, which we will come to in just a moment. Okay? So volume is replicated across servers. Multiple logical volumes may map to the same physical volume. Basically, there's a concept of a logical volume which we will not go into a whole lot. Okay? And files have some sort of an identifier that the file system uses to track down the file. The identifier basically includes, think of it as a server ID and a file handle. Okay, so there is you have to base in a file, when you present a file handle to the file system saying I want to access this file, it includes or it encodes two pieces of information. One is what volume is it stored on. Okay? There's a volume ID and there's a volume map, as you will see that here. There's a volume database which allows you to figure out where is this volume. Okay, so it will tell you a list of all the servers that are replicating the volume. You can go to any one of them to get your files. Okay? Because you are replicated. Whenever you want to access a volume, let's say /home, your home directory, you go to this volume database and say where are these volumes stored. If there's only one copy, it will point you to it. If there are multiple copies, you get a list and you can go access whichever one you want. And then there's a file handle that allows you to track down the specific file or the directory that you're trying to access on that volume. Okay? So that's just file identifiers. Now there are more interesting things happen when you think about replication and disconnections and so on. Okay? As far as Coda is concerned, it uses a very simple idea, which is read once, write all. Okay? If you remember when we talked about Gifford's quorum-based protocol, where you said you have a write, you send it to multiple machines in the write quorum, and you need to read, you need to go to all machines in the read quorum and read. Okay? In that context, I said there's a special case where if you wanted to read from exactly one machine and always have that file being returned to you be current, then your only option is every write has to be sent to all members of the quorum. Okay? And that is what we call read once, write all. Okay? So this is an example of a system that uses the same idea from a quorum-based protocol where every write to a file is sent to all the volumes all volume replicas. So now when you want to read, you can go to any one of them and you're guaranteed that they are the most recent. Right? Okay? So barring network partition, of course. So here is basically what happens. Every write is going to all. In this case, there are three servers, S1, S2, S3. They all have a copy of the volume and all files are replicated in three locations. Every time a user updates a file, that write is sent to all three replicas. Every time you need to read a file, you can go to any one replica and you get the most recent version. Okay? So that's basically how Coda is going to handle replication. Now the problem arises when you have a network partition. Okay, so here is an example where you see that there is a network partition. That means that S3 has gotten disconnected from S1 and S2. They are still on two networks because the network link between S1 and S2 and S3 is broken. Okay? So some clients continue to access S3. Here is a client B that's accessing S3, and some clients continue to access the other two volumes. Okay? So you may get a scenario where two different clients access the same files in two different partitions and update them. Okay? So your client B may access file foo and change it, and client A may also access file foo of these two servers and change it. So now you have a problem because you have a write-write conflict. The same file has been updated by two clients independently, and these two clients cannot talk to one another, neither can the servers talk to one another because the two networks they are on have gotten a disconnection. There's a network partition. Okay? So what can Coda do in such scenarios? Okay, so all you can do is actually detect that such a scenario has actually occurred. Okay? So you have to detect write-write conflict and flag it to the user, saying something has happened. This is equivalent to when you change some file, source code files in the source code repository, you may get a conflict often. If two users go and update the same source file and you check in your commits, you are going to get a conflict saying user has modified something, and you may have to go and reconcile. Same philosophy. Okay? So you have to first detect that there is a conflict, tell the user that there is a conflict, and force what is called a manual reconciliation. Saying this file has been changed. The file system doesn't know which of the changes, which change should be thrown away, which change should be kept, should it be merged, none of this is known to the file system, so you ask the user to deal. Okay, so that's the philosophy, but you still need to know how this conflict occurred and when it occurred. And the way this is done is you basically keep what is called a version vector. Okay? Version vector is kept by each server. Okay? And it tells the server every time you see an update, you increment your version vector. It's almost like think of it as I shouldn't say a logical clock, but it is similar concept where you basically increment a counter which says how many, every time you change the file, you increment a counter. Okay? And you also, depending on who else has seen the writes, you will increment their counter. So let's say that initially the version number of the file is version 1. Okay? So all three servers here are version 1 of the file, S1, S2, S3. So the version vector is 1, 1, 1. Okay? Then a disconnection occurs. Okay? So now you're disconnected. Server S3 has the same version, which is version 1, and S1 and S2 also have the same version, which is version 1. Okay? Now B goes and updates that file. So server 3's version increments to 2. Okay? Server 3 tries to send that update to server 1 and server 2 and finds that they are unreachable. Okay? So it basically can only increment its version and it cannot send those changes to S1 and S2. Okay? So as far as it is concerned, the version vector now is 1, 1, 2 because it knows that its local version has been updated to 2 and it hasn't sent those changes to the other system, so it knows something has gone wrong. So it will say that as far as I know, these other two systems still have the old version of the file. Client A does the same thing, it goes and updates the file. Now S1 and S2 can increment their versions, okay, but they cannot send it to S3 because of the disconnection. So you will see that as far as S1 and S2 is concerned, they will assume that the version of the file is 2 to 1. Okay. Now when the network partition heals, which means that the network is, this problem goes away, these servers are going to try to resynchronize, saying what writes did you see during the disconnection. Okay? And this is done simply by comparing version vectors. So you will see that these two version vectors are not comparable. They actually flag a conflict saying during a partition, these two servers saw a write and this other server saw an independent write. Okay? So that is going to flag a manual reconciliation because that will be a write-write conflict. Okay. Now, if only one of these two partitions saw a change, then the problem is easy because let's say S3 saw it, but S1 and S2 did not see any updates to that file. Their versions will still be 111 and this version will be 112. So now this version strictly dominates this change. So then S3 will say, I have a newer version of the file, take it and simply send it to you. And then the versions will be automatically reconciled. Yeah, so in this case, so there's no write-write conflict. Write occurred only in one partition, not the other. So you simply send the changes and everyone has the most recent version. But if both partitions saw it, you flag a conflict. Okay, is that clear? So this is just doing pairwise comparison, similar to what happens in epidemic protocols. Okay, if you remember, when I was talking about eventual consistency, either servers contact each other, they see which writes have, where have writes taken place, and they simply get more recent version. This is essentially a way to implement eventual consistency. Okay? Except that during network partition, at other times you are actually trying to send the versions immediately. When the network partitions, the only guarantee you can give is eventual consistency, which says when the partition is healed, we will reconcile and everything will be consistent. Okay, so that is server reconciliation, or rather manual reconciliation during server replication. The other thing that Coda does, as I said, is that you also keep a copy of all the files on your mobile device. Okay, here the copies are kept on 3 different servers, and now you assume client A is a laptop and client B is a laptop. So client A itself can disconnect from the network. Okay, that's not a network partition. You just walk away from your Wi-Fi network. You don't have any network connectivity. Okay, in that case, what client A is going to do is it's going to keep a cache, and that is a copy of all the files that the user of client A frequently accesses. This would be copy of their home directory, copies of any applications they access, whatever A likes to access frequently is cached on A's machine. Okay? And the same protocol is going to repeat. If A gets disconnected, okay, the machine, A's machine will pretend like it's connected, but now you have only access to the cache, not to actual servers. Okay? So A's machine is going to pretend as if the server is actually online, but all reads and writes are going to the local cache. Okay? You are going to do the same thing. You are going to keep version vectors of whatever changes are made and so on. And when you reconnect, you are going to run the same protocol. Okay? And this is the protocol that is shown in the next slide, which is the disconnected operation protocol. And so what this says is that a device, a laptop or any mobile device for that matter, can always be in one of 3 states. Okay? That's holding, emulation, and reintegration. Okay? When you are in holding state, this is when you are connected to the network and you are actively downloading stuff into your cache or your hold. Okay? Then I may disconnect at any time. I'm connected at this point. It's time for me to keep downloading any changes, the most recent version of the file, so that if you get disconnected, you have a copy of whatever the user needs locally. Okay? That's the holding state. Okay? As soon as you disconnect, you go into emulation state. In emulation state, your client pretends like you're connected, but obviously you're not. And the file system now starts sending all reads and write requests to the cache instead of sending it to the server. Okay? So from the user's perspective, nothing has happened. It looks like you're still connected and all your files are still accessible. You can start applications, you can open files, you can modify them, do exactly what you did. Okay? The only issue is if you try to access a file that is not in your cache. Okay? So this is where you have to be careful, and that the user has to either specify preferences to the file system saying, I frequently access these directories. Okay? Keep a cache. Okay? Or the system will learn based on whatever you are accessing over time. It will say, previously you did not access this application, but now suddenly you are accessing this new application. Let me make a copy. The system will learn, users can specify preferences. So long as both of those things are done well, most of your frequently accessed files will be in your cache. Yeah, that's the assumption. And we assume that you have a large enough disk that you can keep all your typically accessed files locally on disk. Okay? Because disks are large and disks are cheap. So you go into emulation mode where user continues to access their files, make modifications and whatnot. Okay? At a later point, the user goes back to a network and plugs in their laptop into or reconnects. Okay? So then you go into reintegration mode. In reintegration mode, you are going to run a reconciliation, saying while the machine was disconnected, did the user make any changes to the files? Okay? If so, you send them off to the server. You ask the server, while the user was disconnected, did anyone else make changes to files they frequently cached? And you re-download. So you run a two-way synchronization. Okay? You may see a write-write conflict at this point. Okay? In that case, you have to tell the user, say you modified this file, some other user modified the file on the server, that's a conflict. Go figure it out. Okay, user has to decide. The system can't do that. If there was a change in only one of the two locations, then the newer version replaces the older version. There's no conflict. Okay, just an update. If there are changes in both locations, the server and the cache, that's a write-write conflict. So that is what you're going to essentially do. So once you reintegrate, you go back to holding state. So you are going to cycle between these states. Any questions on this? So this was actually a very early version of how you can implement support for disconnected mode. Okay, today you see these ideas, although Coda itself is not used in any commercial setting. The source code is actually available and is part of the Linux file system, so it's free, but it's not frequently used. But these ideas are implemented in lots of different contexts. Okay, so if you have cloud-based storage, things like Dropbox, same idea. You may be connected to your Dropbox in the cloud, you may be disconnected. While you're disconnected, or to whatever is in your Dropbox is still on your machine. Okay? Some other client can make changes and it can get uploaded to the server. Okay? And then when you reconnect again, you're going to have the same reconciliation, and you see that if two users make changes to the same file, while you're disconnected, it throws a conflict. It will actually create two copies of the file with a label saying conflicted copy, and you have to go figure out what happened and reconcile. Okay? So these ideas live on in many different contexts. Right? Whether it is you take pictures of your phone and your cloud-based photo storage and you re-upload them and reconcile, or whether you use cloud-based storage techniques like Dropbox or Box. All of these basically use similar principles. Okay? So the ideas have lived on and been adopted by the system, but this was one of the early ones. It's almost 20 years old at this point, the first version of Coda. Any questions on this? Okay, so that's Coda. Okay, there's one more couple of other things that I wanted to mention here. One important thing that Coda implemented was they had this notion of a transactional semantics. Okay, so it is also another early example of a file system that implemented this notion of a transactions and sessions. Okay, which, as I mentioned, transactions typically used in databases. But here's an example of a file system that used transactional semantics, which basically said while the file is open, there's one large transaction. When the file is closed, either you have to commit all the changes or roll everything back. Okay, if you have a write-write conflict, you can actually roll things back or force manual reconciliation. Okay, also, if there are changes happening on multiple servers or multiple machines and a server, transactional semantics ensures serializability. They ensure that changes to files are made in a certain sequential order, even though changes are actually being made concurrently. Okay? All of the database concepts that we talked in the context of distributed transactions are actually implemented in this file system. Okay? It's a somewhat rare case of file system implementing transactional semantics. Typically, you don't see this being implemented at the file system level. Okay? So that's something to keep in mind. Okay. There are, of course, other cache consistency protocols that are also implemented in Coda. This is a complicated picture, but all that is saying is if a user makes a change to the file and then that change is sent to a server keeps track of which other users have actually cached a copy of the file, and you send invalidate messages saying whatever you have in your cache is no longer valid because some user changed that file. Okay, so it uses, so that's what is shown here. That's the only important part here, which is there's an invalidate callback that is made. So what this also says is that files, the server is stateful. It keeps track of which users have cached what files. So if some user modifies a file and others have cached it, you can tell those other users caches saying file has changed, please download a new copy. Whatever you have is now outdated. Okay, so, and this can only be done clearly when users are connected. If you're in disconnected mode, you can't send invalidate messages to users. But while you're connected, these are kinds of techniques that Coda would use to ensure all the caches have fresh content. Okay? Okay. So that is Coda. We are going to switch gears and now talk about another file system called XFS. And in that context, we are going to talk about two different concepts, RAID and log structure file system. Okay, so first, what is XFS? It's actually a file system that was developed as part of a research project at Berkeley It was done in the 90s. It came after Coda, but it had a very different philosophy. Okay, X here stands for no server. Okay, X is like you crossed out the server. Okay, in that, basically their philosophy is this is a file system where there is no client and no server. Anything can be stored on any machine, okay, and we'll still make it all work. And the basic philosophy was disks are large, lots of machines have lots of disks. Why only keep all my files on a server and waste the disk space on other clients? Let's use all the disk space on all the machines that are connected. Okay? And if that is the case, then you basically have lots of machines that are somehow pooling their storage together. And you store content or files on any machine and you can access it from any other machine. So the whole concept of having a distinguished server is gone. Okay? Any data can be stored on any machine. Okay? So there is no real client or a server, except that when you try to read files, you're a client, and when you store someone else's files, you're a server. So each machine is both a client and a server at all times. Okay? So that was the philosophy for XFS, and so it basically they did not want any centralized entity in their file system. Okay? So if you have a client server, you have a centralized server or set of centralized servers if you are replicated servers like in Coda. They said, let's do away with a centralized architecture completely. We'll have a completely distributed architecture, which also means it's a serverless architecture. Okay? So it's an interesting paper to read, and I'm going to put a link to the paper. It's actually a nice paper. It has lots of interesting concepts. I am going to only hit two high-level issues in XFS, which is this notion of how data is actually stored on multiple machines, and the second is how you can optimize for certain common characteristics, which is more writes than reads. Okay? Now, because you have multiple machines, you have to deal with the possibility that some machines may fail. Okay? And if some machines fail, you don't want data that was stored on those machines to be somehow disappear. So we are going to come up with some scenarios where even if some machines go away, the data remains accessible. Okay? That's the first thing we have to deal with. Okay? So there are two issues that we will do, techniques that we are going to use. The first is we look at this notion of RAID, which you may have heard of. Okay? RAID stands for redundant array of independent disks. I'm going to first talk about the high-level concept of RAID, and then we'll come back and see how XFS is actually going to implement a software version of RAID. Okay? So XFS uses RAID in order to distribute all of its file on multiple disks. So let's first talk about RAID, and then we'll come to talk about caching and all of those other things. Okay? So the main concept in a RAID-based storage system is that data from files are stored on multiple disks and possibly on multiple machines, okay, which is a very different way of organizing your data. Okay, I'm going to draw a picture here. Okay, so let's say you have a server. Okay, we're going to step away from XFS for a moment, just talk about RAID independently from XFS. Let's say this is your server. Okay? You have two disks attached to the server, disk 1 and disk 2. The standard way of doing things is to implement a file system or a volume on each of these. Okay? If you have Windows, you'll say this is my C drive and this is my D drive. Okay? If this is Linux, you will put some, let's say, /user here and / something else, some other set of directories here. So they are independent disks. Okay? Each file in this normal case is either stored on this disk or this disk. Okay? That's how you typically store data when you have multiple disks. Okay? RAID does away with this concept and it uses a concept called striping. Okay? This is a fundamental concept that you need to understand when you go from a single disk to a multi-disk scenario. Okay? So what does striping mean? I'm going to show you a picture here. Okay, so let's assume rather than one now there are 3 disks or 4 disks. Okay, so if you have 4 disks on your server, rather than storing each file on a single disk, we are going to take our file, okay, we are going to chop it up into disk blocks, okay, and then basically store blocks in a round robin fashion on all the disks. Okay, so block 1 is going to go on disk 1, block 2 on disk 2, block 3 on disk 3, block 4 disk 4. So you just round robin. Okay, take a file, chop it up into blocks, and then store each block on successive disks in a round robin fashion. This is called striping a file across multiple disks. Okay. So now you can ask, what does this give us? Why did we do this? As opposed to taking one file and storing it here and taking another file and storing it on some other disk. And so, what does striping give us? What did we get out of this? Do you have any thoughts on that?
You are reading and writing faster.
You are reading and writing faster. Why is that?
Because the disk read and write slower than the memory.
Okay, disks are slower than memory.
So when you want to read a file, so you have 4 parallel come to the memory.
Okay. So first thing you have to realize is doing this gives you parallelism. Okay. If you take a file and you say, I want to read this file, whole file, I can send 4 independent requests or n independent requests to all of these disks. So now I'm getting n times the throughput if there are n disks in the system. Okay. So this is essentially treating this as a set of parallel disks that I'm accessing all at once. Okay. So when I write, if I have to write 4 blocks rather than sending all of that writes to one disk, I can send them to multiple disks. So I'm getting parallelism, potentially higher throughput. Okay. So that is the first advantage. Okay, is parallelism. Okay, what other things can you see here? Anything else?
The redundancy, if one of the disks fails, then you will only lose one block as opposed to all 4. If you were to store all 4 blocks on the same disk.
Okay, we'll come to failures in just a moment. Okay, just hold off on that. I'm going to talk about failures and what happens when disks fail. But in the no failure case, are there any other things you can think of here? Yes.
If multiple pads are accessing the file, then you can distribute the load across.
Okay. So the other thing, as is pointed out, is you get load balancing benefits. Okay? If you actually stored entire files on individual disks, you have to somehow figure out a way of balancing that load. Okay? You don't know when you create a file how popular a file is going to be, how many users are going to access it. So it is entirely conceivable that files stored on some disks are less accessed than files stored on other disks. So some disks may get more heavily loaded than other disks. Okay? If you just store entire files on disks, because you don't know when you create a file, neither you nor the file system knows. If you just arbitrarily stick it into whatever directories and so on, you may get load imbalances in the system. Okay, some files may be very popular, but they are stored on some disks that get heavily loaded. Other disks may be sitting there idle. Okay, so now when you stripe, you will see that the load is always distributed. Since all files are stored on all disks, it doesn't matter which file is popular and which file is not. All popular files are going to send their load to all of those disks, and you are fine. So you are actually using all of the resources and not causing load imbalances in the system. So you get parallelism and better load balancing properties. Okay. Those are the pluses. Okay. Okay, now let's take a scenario of what happens if my disk fails. Okay, so you may have n disks and one of them goes down. Okay, let's say this disk is failed. Okay, so the question is just how does this scenario compare with the striping and the no striping case? Okay, let's take the no striping case where individual files are stored on individual disks. Okay, if this disk fails, okay, if you haven't done anything to keep a copy of the data there, all the files that were stored on that disk are gone. All the data is lost. Okay, but all of the files that are stored on these other 3 disks remain accessible. Those disks are not failed. Okay, so let's say 1/4 of you stored n files, 1/4 of your files have gone, the 3/4 of your data is still intact. Okay. Now, what happens if you stripe all the files and one disk fails? Okay, if you basically stripe all your files, 1/n of each file is gone because you're storing all blocks of the file on all the disks. Okay, so if this disk is gone, some blocks of every file have disappeared. That essentially means that every file has some missing data, so all files are impacted by this. Okay, is that clear? So if you actually just do striping and don't do anything better than striping, your fault tolerance properties actually get worse in that all data gets impacted if any disk fails. Whereas in the previous case, in our old regime, some of your files are gone, but the other files are at least there. Okay? Here all files are missing data. Yeah, that essentially means all files are useless, or you lost all of your data. Okay? So that says that just striping, which gives us these two properties, which are good properties, is not good enough, because if you have any failure, all of your data is going to be impacted. So you need to do better than that, and that is where our redundancy is going to come in. Okay? So we are going to see how to make it redundant. That's what RAID is actually going to do. Okay, and just to give you a little bit of sense of why this becomes important, so you will, if you look at some of the sort of the reliability figures for disks and try to do some calculations, you'll see that there is a problem. Here is 50,000 hours is a typical lifetime of a disk, which is several years. Okay, if you buy a disk, you expect that on an average it's going to last several years and it's going to die eventually. That's a typical lifetime of a disk. If you build a server with 70 disks, which is not even unusual, okay, because disks fail independently, the probability of a failure that any disk is going to fail is actually going to be that over that. Because disks fail independently, the probability that there's no failure is 1 to power p minus n. If you remember where I said of as go to infinity, this ratio is going to start tending towards 1. This is what you'll see here. So if you have 70 disks, the mean time to failure has now become 700 hours. Okay, that's 1 month. Okay, so you went from independent disks failing or having a lifetime of 6 years to some disk failing to 1 month. If you have 70 disks, on an average every month some disk is going to fail. Okay. So that's not good, because if you basically buy a big server with 70 disks, put all of your data, next month one disk has failed, all your data is gone. Okay. So you cannot actually live in that regime. So without redundancy, the system becomes too unreliable. It's no longer useful to us. Okay. So we have to now balance these benefits of parallelism and load balancing with some sort of redundancy that will ensure that the system continues to run even though disks are failing. Okay, so that's the motivation for why you need redundancy at all, because as you keep growing the number of disks, the probability that something is going to fail is going to keep growing. Okay, in the common case, some disks would have always failed, and you need to actually ensure that you will have some redundancy. So what can you do? So that depending on what kind of redundancy you build, there are different types of RAID systems. Okay? RAID 0, okay, which basically says no redundancy, is essentially only disk striping. Okay? It says there's no redundancy. You simply take a block of the file and just chop it up into, take a file, chop it up into blocks, store them in round robin order. Simple disk striping, no redundancy. It's called RAID level 0. Anything greater than level 0 will have some level of redundancy. Okay? RAID 1 is the simplest level, which is called mirroring. Okay? Mirroring, what does mirroring say? Mirroring says that for every disk in your system, there's a backup disk. Whatever you store on the main disk, you always store on the backup disk. If you write to the main disk, you always have to write the same thing to the backup disk. Okay, so now if that disk fails, its backup disk is always available, and automatically the system will switch over to the backup disk. Okay, so this is called mirroring. You keep a mirror copy of whatever is on one disk, you keep a mirror copy on a second disk. Okay, so that's the simplest form of redundancy. Okay, so the simple good thing is very straightforward. You will still stripe, except that now what is going to happen is your system will be chopped up into 2 parts. So you have your 4-disk system. Because so you basically say this is the primary copy and these are the mirrors. So this disk mirrors this disk, that disk mirrors that disk. So now you are going to just stripe between these disks, and then whatever you do here is also happening there. Okay? If any of these disks fails, you go to the mirror to get those disk blocks. Okay? So now if your disk fails, then there is no problem, because there's always a backup disk. Okay? Except that the downside is you just doubled your hardware costs, or you halved your storage capacity. So you buy 10 disks, you can effectively only use capacity of 5 disks, because the other 5 disks are sort of mirroring whatever the first 5 disks are. So you basically cut down your storage capacity by half, or you doubled your hardware. If you need 1 terabyte, you need to buy 2 terabytes of storage, okay, just so that you have a mirror copy of everything you store in the system. Okay, so what could you do to make this better? Anyone know anything about RAID? So you will have to do better redundancy. Okay, you cannot do away with redundancy. You can't say, this is too much, I'm doubling my cost, so I cannot do without it. So you cannot live with data loss either. So you are going to do better. Okay, what do you mean by better? You're basically going to, not going to go into animation here. So you are going to use things called error correcting codes. Okay, so these basically says you will have redundancy, which means if a disk fails, you'll still be able to get back the data that was on that disk. But you're not going to just go and simply store a copy and double your hardware, because you're going to store other types of information that will allow you to reconstruct. Okay? And this is the simplest thing that you could do is what is called parity. Okay? What parity basically says is, if you have some number of data blocks, you are going to store an additional block that stores extra redundant information. And here is an example of what is done here, which is also shown here. So you have data blocks D0, D1, D2, and D3. Okay? You do an operation over those, you compute one extra block called the parity block that is stored there. Okay? And the way you do this is you basically do D0 XOR D1. So you take these blocks, you simply XOR them. I presume you all know what XOR is, right? So you simply XOR them, and what you get as the result you store on that block. Okay. Now, if any of this disk fails, let's say this first disk is gone. Okay. So you want to now read D0. Okay. You haven't actually kept a copy of D0 because this is not mirroring anymore. But what you can do is, because D1, D2, D3 and the parity block is available, you can reconstruct D0 on the fly. Okay. The way you are going to do this is essentially that. That's a simple property of XOR. If you don't have D0, you can simply read D1, D2, D3 and the parity block and XOR them, and you're going to get D0. Okay. This comes from the simple property of XOR, which says that if A XOR B is C, okay, and if either of these is not available, then what you have is B XOR C is going to give back A, or A XOR C is going to give back B. If either of these two original items are not available, you can take that and XOR them. It will give you the rest. Okay, this is a simple property of XOR. There is not any rocket science here. And you can just do that for any number of items. So if you XOR n things and you get a result, if any of those are not available, you can store the parity, replace that by the parity, and you'll get back the original. Okay? So what this is saying is, if this disk has failed, okay, just to get whatever is stored on that disk, if a read request comes for that disk, you're simply going to read all these remaining blocks, which is called the parity group. That's the group of blocks that are protecting that block. Okay? And you just XOR them, that gives you back. So on the fly, without even doing anything, you just recovered whatever was on the stored disk or failed disk. Okay? So this is called RAID 4, okay, where you have a special parity disk. Okay? So now the level of redundancy has gone from one disk for every disk to one disk for k disks. Because you can decide what this parity group is here. These are 4 disks are data disk, 5th disk is a parity disk. So you are basically only essentially using 20% of your storage to store redundant data, not half of your storage. You can make this parity group bigger. You can say 10 disks are protected by one parity disk. In that case, you're only using 1/10 of your storage capacity for redundant information. Okay, you can change whatever size you think is appropriate for your system for protecting this. Okay. So this is RAID 4, okay, where there's a special parity disk, and the only difference between RAID 4 and RAID 5 is, in RAID 5 there is no dedicated parity disk, but these parity blocks are just spread across multiple disks. And the reason for this is, if you actually just do RAID 4 where you have a dedicated parity disk, this parity disk is going to become a bottleneck. The reason it becomes a bottleneck is anytime you write to any of these blocks, D1, D2, D3, D4, you have to recompute that XOR and always restore that parity block. Okay? So this parity disk gets the write load of all the other disks in its group. Okay, if there's one write, each independent write coming to these 4 disks, there will be 4 writes here. Okay, it will get k times the writes of all the other disks. So it will become a bottleneck because it has the highest write load of all. Because anytime you update any of this, it goes without saying you have to update, recompute the XOR and store the parity block. Okay, so that says every write on any of this disk is also a write there. Okay, so essentially that disk is going to get the sum of the write loads of all the other disks in this group. Okay, that makes it a bottleneck. Okay, and how do you solve that problem? You solve it by saying there is no parity disk. So here for this group you store the parity here. For this next group you are going to simply put the parity here and store D7 there. Okay. For the next group you'll store the parity on this disk and store the other 4 blocks. So you're just going to distribute the parity, which means that the parity write load will also get distributed. Okay, so no dedicated parity disk. Okay, so that is essentially what is shown here. Okay, so you'll see that your write parity disk is gone. You have D2, so D0 to D3 you store the parity there. For the next group you store it here, so on, and then you repeat. Okay. And it's the same concept. If any of these disks fail, okay, then if you want to read, let's say this disk is gone, if you want to read D4, you're going to read D9P, D10, D11, XOR them, that's going to give you D4. Okay? Questions on this? So you're still doing striping. Okay? Each file is chopped up into blocks and you're going to store them in round robin fashion, except that now if a disk fails, you're going to have some redundant information to deal with it. Now, I should also mention that this is only going to handle one disk failure. If 2 disks fail, okay, you are in trouble because there's no way to recover anything. Okay, this is going to tolerate 1 disk failure per parity group. This is why I said you can make the parity group larger or smaller. If you make the parity group 100, okay, and 2 disks happen to fail, then you are in trouble. But if you have 2 parity groups of 50 each of those groups can have a handle independent failures. If you have 10 parity groups of 10 each parity group can handle 1 failure. So that means you can have 10 concurrent failure, 1 in each group, and you'll still be okay. Okay, so this is why you have to decide how to choose your size of your parity group or how many disks are being protected by a parity block intelligently. It depends on the size and how risk tolerant you want to be and so on. Okay? But multiple failures within the same group cannot be handled. Okay? For that you need more sophisticated error correcting codes which will essentially store extra information to handle 2 disk failures or k disk failures. That we will not go into in this class. Okay? That you can, if you know anything about error correcting codes, you will say if you lose k out of m bits, you can still reconstruct. Okay? So those are all more sophisticated versions. The parity is the simplest of error correcting codes that only uses XOR, nothing more. But there are more sophisticated codes out there that will allow you to tolerate multiple concurrent disk failures within each group of disks. Is this clear? Okay. So that is RAID. Practically all storage servers that you will see that are multiple disks will use RAID. Okay. They'll do this automatically for you. Okay. Basically, when you give it a set of blocks, they'll stripe it, they'll compute the parity. If the disk fails, automatically the RAID controller will say, this disk is gone, let me read the other blocks, let me reconstruct. So there's hardware there to actually accelerate XOR. Okay, you don't have to necessarily do this in software. So that's one concept in XFS, which I'm going to skip all of that. So the thing now coming back to XFS, okay, we sort of digressed and went into RAID so that you now know what RAID is. What XFS does is it implements RAID in software where it is using a disk on each of the servers and it's using them as a parity group. Okay, so now the disks are no longer attached to one server. We are back in this world where we have n machines. We have a serverless file system. So what we are going to do is the following. Okay, so you have a machine 1, machine 2, machine 3. Let's say each of them have a single disk. Okay, you want to store a file foo. Okay, let's make a 4 point here. Okay. What you are going to do is you are going to chop it up into block. You are going to store the first block on the disk of the first machine, second block on the disk of the second machine, third block here. This is going to be your parity, and then the fourth block is going to go here and so on. So you are going to do what happens across a set of disks within a machine. Now you are doing this across machines. Okay. RAID typically says all the disks are actually attached to the same server, and you are doing all of that in hardware. You have a hardware RAID controller that does this. XFS is implementing the same RAID concept in software. You're doing networks. This is called network striping. Okay. You're striping a file across a network onto multiple disks, okay, rather than striping across disks attached to the same machine. Okay, again, you have to ensure that you will have parity and so on. Okay, so think of implementing RAID 5 across a set of machines. So now if any machine goes down, I can still reconstruct what's on there by using the data on the other machines and all the parity used on. Okay, this is called software RAID because you're doing this in software by striping across and doing the XOR computation in software. Is this clear? Any questions on this? Okay, so this is referred to as network striping. Okay, there are lots of other optimizations you have to do, okay, which I did not go into. Okay, so one thing that is mentioned here is this notion of expensive small writes, okay, which is a problem in RAID because if you try to write 1 byte, okay, to a file, okay, let's say you want just type this, you go and modify 1 byte here. Okay. To write that byte to this block, you actually have to now read all of the parity group, okay, update this block, recompute that parity because you have to do an XOR. To do the XOR, you need all the other blocks of the file. You're going to recompute the parity, and then you're going to write this block and the parity block. So this in the RAID world is called a read, modify, write cycle. Okay? When you're small writes, you have to read the entire parity group. So to write 1 byte, I have to read n blocks. Okay? I have to then update the block that I'm writing to. Okay, that's the write. And then I'm going to recompute the XOR, and then I write 2 blocks up. So 1 byte has resulted in n plus 2 IO operations, okay, which is expensive in the RAID. Now, if you're going to do a large write, if you're going to write 1 megabyte, that's great because I don't need to read the old block. I simply, because they're all going to be overwritten and there's nothing to read, I simply compute a new parity and just overwrite the old blocks. Okay, so large writes are cheap. I simply recompute it because all of them are already given to me by the application. Here is 1 megabyte, write it out. I just simply compute the parity and I overwrite the old block. Small writes are very expensive, okay, because you have to do a read, modify, write cycle. So then you have to then employ caching to ensure that some of these operations become cheaper and so on. Okay, so these are all artifacts of RAID, but they get worse in XFS because you're doing network striping. You're not even reading blocks of files on the same machine. I'm going to send all sorts of requests to all sorts of machines, get data, recompute, send them over a network and so on. So that makes things even more expensive. Okay. So that is the first concept. Okay. Second concept in XFS is what is called a log structured file system. Okay. This is another interesting concept. So log structured file system was another file system that was actually developed in Berkeley. It preceded the design of XFS. Okay. XFS implements a log structured file system as part of its network striping layout. Okay. So I'm going to now do another digression and tell you a little bit about what an LFS file system is. So actually a very interesting file system. Okay. You need to at least know what LFS based file layout is. Okay. And I'm going to draw a picture again to show what this means. Okay. So again, forget XFS for a moment, and we are going to simply take a single machine, okay, not even multiple machines, okay, and just look at, let's say, one machine, one disk. Okay, this is disk, that's RAM, here's an application. So let's just take a typical file system for now. Okay? Applications read and write data from the file system. They read and write files. Okay? Now the operating system wants to improve the performance of I/O because disks are slow. It will typically employ an in-memory cache. Okay? Every operating system that you can think of will actually have a file cache for the file system. Okay? Because the disk is slow, anything that you read recently will be stored in the file cache. If the application accesses that data again, you'll read it, you'll respond on the cache rather than going to the disk. This gives you better performance because you're no longer getting slowed down by disk I/O. Okay. So now if you assume that you have a file system cache that is helping you improve performance, you can ask the question, what is the impact of that cache on the traffic that the disk is going to see? And let's make that more clear. Let us say that applications issue equal number of reads and writes. So 50% of the requests are reads, 50% of the requests are writes. Okay? All requests are going to hit the cache. Okay? And let's assume your cache is performing well and you have a high cache hit rate. So then the question is, if 50% come here as reads and 50% writes, what is actually trickling down to the disk if you have a high hit rate? Is the question clear? What I just said. So assume that as an set of applications. If you don't understand this, you will not understand the motivation for XFS. So this is the only part that you really need to understand. Okay, your disk, okay, that's as a file system. There's an OS that maintains a memory cache that stores all of the recently accessed blocks from the disk in the cache. Applications are sending reads and write requests to your files. Every time a read or write comes in, you first look at the cache. And then if it's a cache hit, you're going to service the read from the cache. Otherwise, you have a cache miss, you go to the disk and read it. Now, if half the requests are reads and half the requests are writes and they all hit the cache has a high hit rate, what is the traffic that the disk is going to see as a result? Yes.
The disk could have low traffic since all the hits are going directly to the cache. I'm not sure.
Okay. So you're partly there. So first thing you have to realize is some of the requests are going to get filtered by the cache. So whatever is a cache hit, the disk is never going to see. Okay. So some of this, so if you have n requests, only some fraction of them are going to the disk at all. Okay, that's number one. Okay. Number two, you have to distinguish between how a cache is going to handle a read and a write. Okay. If you actually wrote to the file, even though you may first write to the cache, eventually that write has to go to the disk because you're written to the file. You can't just keep that in memory, some persistent storage. Okay? So it may get delayed, but all the writes are going to trickle from the cache into the disk. Okay? Simply because if you write a file, you have to eventually the data has to be put on disk. Okay, but reads are never going to get to the disk. If they get absorbed by the cache, the disk is never going to see those reads. Okay, so your cache is going to filter your requests. Okay. Number two, most of the filtered requests are going to be reads, not writes, because by definition, all writes have to eventually hit the disk. You may buffer them for some time, but eventually you're going to flush those writes to the disk. So what does this mean as far as the disk traffic is concerned?
Maybe 50%.
Okay, so basically your disk traffic will be mostly write dominated. Because you have put a big cache and the cache is absorbing most of your reads, if you actually look at what is going on in a typical disk, most of the requests that are hitting the disks tend to be writes. Occasionally your cache misses for the reads, that will trickle, you'll read the data, you'll put it in the cache, and then subsequent reads for that block are going to be handled from the cache. Okay. So what is this telling you? If you have lots of RAM and you put a large cache in there, which most operating systems will do, your file system traffic becomes increasingly write dominated. There are fewer and fewer reads that actually trickle down to the disk because most of the reads are handled from the cache. Okay, so this was the main insight behind LFS. They said write traffic is becoming more and more write dominated. Okay. So then the question is, how should you redesign a file system if most of your common case is writes and not reads? Okay, that is going to be the design of LFS. The observation behind LFS is if you put a cache, the cache absorbs your reads, what your disk is saying is mostly writes. Okay? So now if you have a write, so now we should ask the question saying, how do you redesign your file system to be write optimized? Okay, so we haven't answered that question, but the motivation should be clear. So now we want to say, let's optimize for writes. Let's make writes as efficient as possible. How do we do that? Okay? For this, we'll need to go back and try to understand what disks look like and how they behave. So I don't know if most of you know this, but a disk is going to look like whatever your CD or DVDs look like. They have a platter, and you basically the disk is spinning, not SSDs. These are magnetic disks, right? So your disk is essentially like a CD or a DVD. It's spinning, and you're storing data on the disk in concentric circles, exactly how you record on a CD. And there's a disk head. Okay, so if you want to read some block, you have to then move that disk head to the right track where the data is stored, and then you are going to read or write that location. Okay, so what that also means is every I/O request that the disk sees is going to incur what is called a seek latency, where you're simply moving your disk head to the right track where the block that you're trying to access is stored. Okay, so you're simply moving the disk head back and forth until it's positioned on the right track. Okay. And then you're going to wait for the disk to spin until the data you're reading is right under the disk head. Then you can read or write those bits. Okay. So essentially what that means is for every I/O request is going to, if you are reading randomly from disk, every I/O request is going to incur a seek and a rotational latency, where you're not doing anything other than trying to position the disk head to the right place where the data is stored so you can read or write. Okay, so that's basically what you're going to incur. So now we want to see that if all of your requests are writes, how can we optimize this overhead? How can we reduce this overhead? Okay. Can you think of any simple way to write data to your disk, okay, that is going to reduce or eliminate some of these overheads, secret latency, rotational latency, and so on? What could you do? Okay, so the way you are going to eliminate the disk overhead, the only way you could potentially eliminate the disk overhead is if every block you write, you just write sequentially. So there's nothing, nowhere for the disk head to move, because I just wrote a disk block here. Another write came in. Rather than writing it to a random location, I want to write it to the next location. Okay, there's no seek in this case because I'm already there. I'm simply just writing sequentially to disk. Okay, so if I write all of my blocks sequentially to disk, I've simply eliminated all my seek latency. Okay, seek is all gone at this point. Okay, so I'm going to get very high write throughput. Okay, if I wrote to random locations on disk, saying first block got wrote there, second block got, I'm still moving back and forth. I have to move here, right, then I move somewhere else, right, and so on. So I reduced all of that latency, or even eliminated that latency by writing sequentially to disk. Okay. So this is referred to as a log. Okay. Log is essentially saying that I'm going to simply start writing sequentially. Why can I do that? Because the disk is seeing very few reads at all. So I'm only seeing writes. If I had a mix of reads and writes, I could not do this because the reads will force me to go and read whatever the user wants to read, okay, which will be in some random location. So I have to incur a seek to go there. Okay. If there is no read, I don't have to seek to arbitrary locations. Writes you can control because you control where you write your data. Okay, you start with an empty disk. Okay, let's say, and you start seeing writes. You are going to just start from the innermost track and keep on writing, okay, until you hit the end. So that's my log. I have just written my log sequentially. Okay, and so I'll hit the end and I'll go back. Okay? Now that's the basic idea behind a log structured file system, saying that let's basically do away with this notion that I can write blocks wherever I want, which is what you have in a normal file system. We say that because the write traffic is dominated by writes, I am going to write sequentially. So that's the first idea. Now there are lots of complications that arise as a result. Okay? What if I wrote let's say I wrote some file, let's say foo.java, okay, that got written there. I open that file, okay, and then let's say it comes from the cache or whatever, I make some change and I write it back. Okay? And right now I am at this point in the log. This is all written and this is empty. Okay? In the normal file system, I would actually go back and update that block because I just made a change to it. But if I'm forcing myself to write sequentially, I cannot do that anymore. I'm simply going to say that I have a new version of the block. I'm going to just write the newest version of foo.java here, and I'm just going to mark that block saying deleted. Because I only have two options if I update a block that I already written earlier in the log. I go back and update it, then I incurred a seek. Because I have to go back to whatever location you wrote to and incurred a seek. or I am here, so I can simply continue writing sequentially. If I continue writing sequentially, I have to mark that bit saying that block is no longer valid. Okay? So now what that means is if you have a long sequential log, you will have holes in between. Holes are all data that have been overwritten or files that have been deleted. Okay? So your log is being written sequentially, but as you keep writing from the beginning to the end, data is being basically overwritten and there are holes appearing. Okay? So the next time I cycle back, okay, I no longer have a nice clean log that I can keep writing. Instead, I have all these holes in between. Okay? So to now eliminate the impact of that holes, I have to run garbage collection. Okay? So the problem with log structured file system, the reason all this sounds great and highly optimized, good performance, the reason they have not taken off is it's like the Java world. Every so often I need to go do garbage collection and compact. Okay? I have to take all this hole, I have to just start shifting the data up and take all the holes and I have a log that reappears at the end. That is all unused data. Okay? Or I basically have larger chunks, I remove unread data, I put them somewhere else. So now a large chunk that's freed up, I can again write it out as a log. So all log structured file systems need garbage collection. That means even if users are not reading or writing, there's a lot of I/O that's going on that just keeps moving data, does compaction. It's like defragmentation. Yeah, so I'm basically just running my defrag all the time, and the disk keeps spinning, and there's nothing happening. I'm not reading or writing anything, but the disk is spinning because you're running this in the background. Because this is the only limitation in log structured file system, which is I need to start cleaning holes. Okay, basically garbage collect holes that are being created by new writes or deletes. Okay, so it's a very nice idea. Okay, it is actually a very nice observation saying here is a right optimized file system and how do you actually make it work and whatnot. The problem is that you have to do garbage collection. Okay. Now everything I've said only applies to magnetic disks. In SSDs there is no seek. Okay, SSDs there are no moving parts. It's just that my entire disk is a linear sequence of writes. You can go and write whatever you want anywhere you want. Okay? So this whole notion of trying to optimize for writes is gone because there's no distinction between reads and writes. Writing to location I is the same cost as writing to the next location where I previously wrote because there is no cost. It's like I have an array. It looks like RAM. I can go and access any location in RAM at the same cost. There's no cost saying I have to now access a far off location and know for more cost than accessing the nearby location. So SSDs don't need log structured file systems at all. Okay? But all magnetic disks do this.
I think for the SSDs, there are write and magnification, right?
Yes.
So I think here the log structured file system, by combining several files into another one, still helps improve the write performance.
In SSDs or what are you talking
in SSDs.
So in SSDs, you use log structured nature for a different reason because you have to do things like in SSDs, you can only write to a block certain number of times before it dies. Right? Because of the way the SSD technology. Magnetic disks don't have that limitation. So you want to evenly write to all of the locations on your disk and age them at the same speed. If you overwrite a block many times, that block will age faster and die faster than other blocks. Right? So you do all this wear leveling and things like that, which is why you use log structured, you write sequentially for many other reasons, not for this reason. Okay? So you don't actually need, you could have any other technique that says write to each block equal number of times, age them all at the same rate. One way to do that is a log. There are many other ways to do it. Okay? Here you do it for a very different reason. Magnetic disks have seek overheads that are very bad. That can kill your performance. Okay, so you are trying to eliminate that totally. Okay. So that's log structured file system. Now coming back to LFS, what you have done here is you have combined software RAID, which is striping, with log organization. So you are going to now just write everything as a log. Your log is now going to be striped. Rather than files being striped, your log is actually, think of a log as a large sequence of writes. It's going to be striped. You're going to have large caches that absorb most of the reads. So you're going to have large writes, which gets rid of your read, modify, write cycles. You have a parity group. You just stripe the entire log. Okay? So you are basically going to combine LFS with software RAID and do network striping in XFS. So this is the high level concept. There are many other details that I just glossed over. The 2 or 3 takeaways are you do network striping, you use software RAID, and you use log structured file system all built into one. Each of these ideas were developed independently. Okay, there are entire lines of research that led to them, but XFS brings them all together. Okay, so that's the takeaway. Okay, I'm going to spend the last 5 minutes talking about Hadoop's distributed file system, which is called HDFS. Okay. So HDFS is another file system that has become popular, but it has a very different use case. It is used for batch application that access large data sets. It is not meant for interactive access where you open a file, you make modifications to it, and you write it back. It's not meant for editing a file or reading mail or so. It is meant for, I have a very large data set. I want to process it in parallel and do some computation on it. Okay? How do I do that effectively? Okay? So it is meant for reading very large data sets in parallel by lots of machines that do some computation. They may write some intermediate results. Okay? But it's a distributed file system optimized for batch application, not interactive application. Okay? It is designed to be fault tolerant, which means if some disks or some nodes fail, you want your data to stay there. Okay, you just put a terabyte data, you can't have half the data or some cost fraction of it go away because the disk has failed. Okay, it is meant for batch processing. Okay, you want it to scale to large number of nodes. Okay. Now HDFS makes an interesting optimization. It says because these are batch application that simply read this data and process it, it uses what is called a worm model, which is write once, read many. Okay. Which also essentially is the equivalent of saying files are immutable. You have your data set, that's raw data, that's not going to change. I may have new data appear which I'm going to append to the end of the data set, but once some data has been produced, I'm not going to change it. Okay, it's going to just stay there. So it is assumed that you are not actually going to keep changing data after you create it. You create it, you can delete the entire data set, but you're not going to go update it like you do normal files. Okay, so this is the idea, and then it also says that you'll move the computation to the data rather than data to the computation. If you can run jobs closer to where data is stored, that's better when you have very large number of servers accessing your data than not. Okay. So there are two principles. The first one is you separate metadata from data. Okay. Many distributed file systems use this principle. The data blocks are stored on a large number of nodes. The metadata, which says where are the blocks of the file stored separately. They could even be stored on a separate machine. In many file systems, there are metadata machines and there are data machines. Okay, whenever you want to open a file, you first go to the metadata machine. The user wants to access file foo, where is the block stored? Okay, so that is simply to keep track of tables which says here, so here are the blocks. So here is your metadata machine in blue. Different machine altogether for the machines that store blocks. Okay, so these are metadata servers that say here is a file. There are 3 copies of the file. Here are where the blocks stored. Okay, and then there are data nodes that actually store data blocks of the file. Okay, that's one takeaway principle. Modern distributed file systems separate data storage from metadata storage. Okay. The second principle in HDFS is because you are optimizing for very large data sets and large writes, you actually store blocks in very large chunks. Okay. Typical file system is block sizes of 4 kilobytes. Okay. In HDFS, you may have a block size of megabytes or tens of megabytes. So you take a 1 terabyte file system, chop it up, let's say, into 64 megabyte chunks, and you store it all in one location. And the reason this is helpful is because you are going to just read lots of data. If you read an entire 64 megabyte chunk, you have reduced the seek overhead. Okay. So you assume that between blocks, you will have a seek. Okay. The larger the block size, the fewer seeks you have because you are going to read a long set of bits without any seek overhead at all. Okay. So in large data accesses or batch mode accesses, you use very large block sizes, okay, that are orders of magnitude larger than your typical file system. And you can get away with this because you are optimizing for very large data sets. Okay. If you use the 64 megabyte block size on your normal file system, you are going to actually make very poor use of your disk because most files are very small. And you create a 4 kilobyte, 10 kilobyte files. If you use a 64 MB block, most of that block is going to be empty and wasted, because you're storing a tiny file in a very large block. Okay. So large blocks only work when you have very large data set. Okay. So the other principle in HDFS is that you use a large block. Third principle is you are going to use simple replication. HDFS doesn't use anything like striping. Okay? What it simply says, you keep k copies of blocks on independent machine. The standard replication factor is 3. Every block is stored on 3 independent machines. You are not going to do striping or any of that, unlike XFS and so on. You just take every block that comes in, you make 3 copies, you put it on 3 random servers. If any 1 or 2 go down, the third block is still available. Okay, so you can handle up to 2 faults in the system. Okay, so 3 takeaways: separation of data from metadata, large block sizes, simple replication over using things like striping, because that will increase my overhead. If I have to read lots of blocks, do XOR, it increase computation. So they take a much simpler philosophy. Let's just replicate k times. That k can be configured. Okay, the default for HDFS is k equals 3. So every block is stored in 3 different locations. Okay, so if you have used Hadoop or MapReduce, underlying it is an HDFS file system, which is, or I shouldn't say HDFS files, a Hadoop distributed file system, which is called HDFS, which is essentially based on these principles. Okay, it's meant more for batch rather than interactive use. So they make different design decisions than you see in NFS or Coda or even XFS. Okay, so we'll end here. We're out of time. This is also the end of the discussion on distributed file systems. Okay, next time we are going to start talking about the web. Okay, World Wide Web is coming up on the next class. So let's